I would like just to relocate where we are and where we go. So you have been studying the demand, and you have been identifying the different types of actions that can be done in order to reduce the building's demand. From there, you have been developing a model that was linking, in fact, the demand with the distribution system and with the way you are going to supply the heat and the electricity to the energy system. So this was then done by developing a mixed integer linear programming model, which allows to decide which kind of technology can be used in order to supply the energy demand. And you have started last week another job, which is going into the details of the optimization by optimizing an investment, the size of a heat recovery heat exchanger, for example, that would allow to understand the compromise that exists between the investment you do by buying heat exchangers, for example, and the savings that you will realize by using the heat exchanger. Okay? And this is where we were last week, discussing about the operating cost and the corresponding capex, which is a capital expenditure that is used to buy new equipment. Up to now, we have always been looking at the heat pumps with a very simplified model. The simplified model that was based on thermodynamics, so we did use the Carnot factor as an indicator of where is the energy, the electricity consumption going as a function of the temperature at which we supply the heat and the temperature at which we harvest the heat. But today, we are, if we have to give an answer about what is if we have to give an answer about what is the best fluid to be used in a refrigeration, in the heat pumps, what are the best operating conditions that corresponds to the heat pump operation, then we are facing the problem of replacing the simplified model with a new one that is a little bit more sophisticated, that allows us to represent what is happening from the thermodynamic point of view, so more than just the Carnot factor, right? It is also allowing us to see what will be the flows in the system, and to some extent to represent what the technologies on the market will allow us to deliver. So what does it mean? It means that we will have to be able to characterize a flow sheet like this one. This allows me to introduce what is first a flow sheet. Okay? And a flow sheet is, in fact, a list of process units. So you have here a heat exchanger, you have here a compressor, you have here a liquid vapor separator, you have here a valve, okay, which are interconnected by flows that are indeed in pipes, if there are flows or material flows. So for example, here, that have some characteristics of states. So for example, here you have a vapor state, here you have a liquid vapor state, here you have a liquid state. So you end a composition. So that means that you have compounds that are traveling in tubes, okay, that are transferred from one unit operation to another one. And what is represented in a flow sheet is, on the one hand, the process units, so the equipments that are used, and the way they are interconnected, so that I will know that the fluid that is coming here is going to cross this heat exchanger, will come here, will change its state, then enter into a compressor, go into another state, receive another flow, which is here the mechanical power, it is another type of flow, so not material flow, but an energy flow, that will then change the state. So here it's a compressed state, vapor state, goes into a liquid vapor separator here, is going to be separated into a gas flow, which is here, that is going to be again compressed in another compressor here, come to a heat exchanger where the fluid is going to be condensed. Afterward, it is expanded, comes here in the liquid vapor state, is going to be mixed first with the gas that is coming here, is going to be separated to have the vapor state, the vapor here, and the liquid here, that is going then to be to do a heat exchange, preheating flow here, and then goes into with another state here, being expanded here, go into the liquid vapor state, and then come back in the cycle. So what I have shown you here is that I have a sketch that allows me to understand where the flow, the material flows are going. And of course, if instead of having one single compound in the system, I can have also a mixture, and there are some refrigerants that you would buy that will be mixtures, meaning that here it's possible that you will not have the same composition here and here, meaning that you will not have the same compression operation here, which then introduces the need for us to understand what is happening inside all the units, because each unit is going to give us, or is going to have a given size, a given type of process operation, and will deliver at the outlet of the unit a flow which needs to be characterized by the flow rate, but not only the flow rate, but also its thermodynamic state. So what is the temperature, what is the pressure, what is the composition of each of those streams. So it means that if now I'm looking at this system here, if I want to be able to characterize the system, I need to know what is the flow at each point here, 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 that is going to interconnect the different process units. Okay? And for doing this, then I'm going to use, I will need models that are going to represent how the process units that are here, like here, it's a compressor, that is going to transform the state from one state to another. Okay, the same here in the heat exchanger. I would like to know I have streams that are entering with a given flow and temperature and pressure composition here and here, and I would like to know how, by doing a thermodynamic operation here that is a heat transfer, I will, what will be the conditions that will be observed here, and what will be the conditions that will be observed here. Okay, so this would be the goal of a model. So this is for a heat pump, okay? But I can also have more complex systems. So for example, this is the flow sheet that is going to convert methane into electricity in a fuel cell, PEM fuel cell. And what you can see here is that you have a collection of process units, the same one, but here we have also chemical reactors, we have still heat exchangers in the system, we have different flows. So for example, I can use air, I can use oxygen. I have different unit operations, so reactors, heat exchange, compressors, turbines, and fuel cell here. That needs to be characterized if I want to be able to design the system, if I want to know what heat exchanger I have to buy and how I have to interconnect, so the pipes that I have to put in the system. Okay, so the same problematic, I need to know the process units and I need to understand the interconnections. Now, if I'm looking inside the process unit, what is going to happen is that I will need a model that is going to represent what is happening, how I do convert the flows that are entering the unit into the flows that are leaving the unit. And here I have to then realize what I know and what I would like to know. And I'm going to, like what we have done in the past, I'm going to add to what I would like to know all the things that I know. Which means that when I will look at this process unit that is transforming flows that are entering into flows that are leaving the system, I'm going to write what I know. And what I do know is, for example, that the mass is conserved. Okay? So it means that the flows that are entering will have to leave the system. The same for the energy. The energy that is entering will have to leave the system. So it means that I have to describe by the equations the mass and the energy balance. And to this, I'm going to add performance equations. The performance equations which are going to tell me to describe what is happening in a system. So for example, the performance equation is going to characterize the heat transfer, okay, which results into the well-known equations of Q equal UA times delta T Lm. Okay, so this is a performance equation. And those performance equations are related to performance parameters. The performance parameters are, for example, the heat transfer coefficient, okay, or the rugosity of the material that is used to create the pipes that are in the heat exchanger. Okay, so those are characterizing what is happening inside the unit that can be used in the performance equations, to which I'm going to add the balances here. And now I have to see how I'm going to make the link between what I know, which is the flow, so it means the temperature, the pressure, and the composition, so the full flow of the different compounds, and the equations that are here. So to write the mass balance is not so complicated. I can write the atoms that are entering have to leave, or the molecules that enter have to leave, and I will have to make to nevertheless identify the pathway that is followed by each of the molecule. And of course, if a molecule enters into a chemical reaction, then I will have to write the chemical reaction that is transforming the molecule into other molecules. So this is related to the mass balance. Now, another problem is going to come when I have to write the energy balance. Okay, because here I do have temperature, pressure, and composition. Okay? But I do not see the energy there. So what would you do then? So I have composition, temperature, and pressure. So what will be your solution in order to be able to write the energy balance?
Relate those states to something like enthalpy and check for
so
the difference.
Relate the state, which is in fact the state variable, so it's the temperature, the pressure, and composition, okay, to something which is enthalpy. So, and how would you do it?
It depends on the kind of material it is, but generally temperature and pressure is enough to determine an enthalpy. Sometimes it's equal to Cp times T.
Okay, so you have said two things, huh? So you know that temperature, pressure, and composition is related to enthalpy. You have learned this in the lecture of thermodynamics. And then you give me another information, is that Cp times temperature.
For ideal gases sometimes.
So it means that you have the impression that there is a mathematical relationship there, right?
Yes.
And then if I told you that the flow that is here is water, and I give you the temperature and the pressure.
And try to figure something out, like whether it's under the saturation curve.
So, and how would you do then? Would you do this then? If I'm asking you to do it today, what will you do? you have, yeah?
I would look in the table.
So you will look in a table, in fact in a graph, not in a table directly.
Oh,
so there are also tables that summarize the graphs, okay? But a priori you will look at the saturation curve to see where you are. So it means that you know how to do it, okay? A priori, if I give you the temperature, the pressure, and the fact that it is water, you will go into a book, find the table or on the internet in engineering toolbox, find the table, the nice graphs that shows the enthalpy as a function of the temperature and the pressure, and you will get the value. My problem is that I would like to do it with a model. Okay, so it means that I cannot ask a computer to read a table or to read a graph. Okay, so I have to teach a computer to read a graph, and this is what we are going to do. So, and for doing this, so it means that if I'm taking the heat pump, okay, I'm going to try to see how I can calculate those points here. So the point 2, that is the outlet of the compressor, the point 3, that is the outlet of the condenser, the point 4, which is after the expansion in the valve at another pressure, and the point 1, which is the saturated vapor that enters the compressor. Okay, so my goal is to be able to make the calculations of all those points. And what I know is that if I'm using another type of fluid, I will have another graph. Okay, so this is 3 graphs for 3 types of refrigerants that can be used in a heat pump. Okay, and of course the points that I had here will not be at the same place if I'm changing the fluid. Okay, so. And something which is interesting, for example, if I'm doing an isentropic compression on this one, you can see that, so it means that I have to follow the vertical line here, I will be in the liquid vapor equilibrium. So I will, if I'm compressing, I will have a mixture of gas and liquid. Okay. While if I'm using this one, okay, starting at the same temperature, for example, I will go here, and I will never enter into the liquid vapor domain. Okay, so it means that the fluids can be really different, and therefore what is going to be happening inside the compressor will be quite different. Okay, if I'm compressing this fluid here, so when I'm starting compressing here, I'm starting to have droplets that appear. Okay, so it means that it's very important to know it, because droplets in something that is rotating, and the system is rotating very fast, is very dangerous, right? So it means that I have to be able to make those calculations. Right, so I need equations. So I need, when we are talking about equations, there was also something that was interesting in what you have said, is that as soon as I gave you the temperature and the pressure, you say, I can calculate the enthalpy. Okay? Which means that there are some things that need to be fixed in order to be able to make a calculation. And here we know that we need to know 2 things. So, for example, the entropy and the temperature. Okay? This is named the degree of freedom of the system. So it's the number of variables that we have to fix in order to be able to solve an equation. Okay? And it's important to know what are the numbers of degrees of freedom of flow, because we need to calculate all the flows, and we have now the conviction that we have an equation that is going to give us all the information that we need, provided that we fix the right number of values. Okay, so what is this number of values that we have to fix in order to be able to characterize the state? So this is the degrees of freedom. That is going to tell us that if you give me n plus 2, n being the number of compounds, and if among the n plus 2 there are at least one variable which is extensive, so that is defining the flow, then I will be able to characterize the state of the system. Okay, so this is the number of degrees of freedom. So n+2 variables are required to characterize the state. Okay, so it means that as soon as you give me the temperature, the pressure, and the flow, and the partial flows, because I have n compounds, then I will be able to characterize the state. If you give me the composition, and there is, so it means it's a fraction, okay? So all the composition -1, plus the total flow, so it makes n values, plus the temperature and the pressure, I will be able to characterize the state. Okay? So, I remind you that this is a question for the exam. What are the number of degrees of freedom that allows to characterize the flow? It's n+2, in which n is the number of compounds, and in which at least one variable is characterizing the total flow. So if I give you only intensive variables, you will not know what is the flow, because you have nothing that tells you the amount that is concerned. Okay? Now the next question is, how do we calculate the rest? So how do we calculate the rest? Meaning that if I give you the temperature and the pressure, you know that you will be able to find in a graph the density. You will be able to calculate the viscosity. You will know which is the type of phase you are facing. You will know the enthalpy. You will know the entropy. You will know the Gibbs free energy. Okay? But now we have to find, so it means that we have to be able to calculate all those values. Okay? And you have also to be able to identify if you are in the gas phase, in the liquid phase, if there is a mixture of liquids, if the two liquids will separate or not. Okay? And you know and you have seen that this depends on the temperature, this depends on the pressure, and this depends on the composition. Okay? And even if you make if there are chemical reactions, okay, you have to know if the chemical reactions will occur or not. Okay? So you have to know that if you mix nitrogen and oxygen, you will not form NOx. Okay? And we observe it around us. And this is what the Gibbs free energy is going to give us as an information. Okay? So it means that we will have to be able to characterize all those dimensions by knowing the n+2 variables that are the degrees of freedom of the system. Okay? So, how do we do this? So the goal is finally to represent what we have here. Okay, this is the Modier diagram for the water. So you have on the one hand the entropy, on the other hand the temperature here. And some people have made experiments that allows us to know that at a given pressure, I'm going to follow this line here, so I'm choosing the pressure, and for a given temperature, let's take this temperature here, I will be able to know what is, so if I'm in this pressure here, I will be able to know what is the value of the entropy. And I will be able as well to know, by following the Eisenthal that are here, I will know what is, by following this one, what is the value of the enthalpy. Okay? And I will even know what is the value of the density, which is shown here. Okay? So it means that this graph is including all what we know. So we see that we can calculate the density, we can calculate enthalpy, entropy. If I have enthalpy and entropy, I can have also the Gibbs free energy, right? So it means that I have everything that I need, okay? And those relationships are defined as being what we will name the constitutive equations. Okay? That's the equations that are going to link all the state variables and the state, when that allows me to calculate all the state variables, knowing the degrees of freedom of my system. So my problem now is to be able to represent in a mathematical form curves, and you can see that the curves are quite special. So if I'm following the enthalpy here, well, it's a special curve, okay? If I'm following the pressure here, you can see that the curve is really special. So it follows this line, at a certain time it goes in here, and then afterwards it follows this line here. So it's not straight line, huh? So it's a nonlinear equation that I'm looking for, and I'm going to look for very special situations, like for example, the fact that there are some kicks here, for example, when there is a phase change that is going to occur. So mathematically, I would say that it's not so easy to do, right? So how do we do this? In fact, we have to represent what is happening between molecules that are in a given state, so in the mixture. Okay? So it means that we have to represent the energy of the different molecules. So the temperature is measuring the agitations of the molecules, and also therefore the interactions, so how they do interact between them. The energy that is between the molecules is also related to the energy that is inside the molecules, mainly because the electrons are rotating around the nucleus, and they are then creating connections between them. And they are also, because they are therefore an electrical entity, creating interactions with the neighboring molecules. Okay? That means that I have to represent what is happening inside and what is happening between the molecules. Do the molecules attract one from the other? And that would be what is happening when I'm going from the gas state to the liquid state. So at a certain time, when I'm going into the liquid state, the molecules are feeling better when they are closer one from the other. So they have attracted, they have been attracted. Okay? And so I have to be able to represent this. Inside inside the molecules, in fact, there is something which is related to the specific heat, which is the vibrations that are between the atoms inside the molecule. Okay, that is going to define how a molecule will respond to the agitation. So if the molecule has not a lot of degrees of freedom, it cannot be shaped in the different directions, and therefore it will not react in the same way as a molecule that has very limited degrees of freedom when we shake it. Okay, so it means that and this is what is related to the specific heat. And then the interactions between the molecule is mainly looking at how the molecules will interact one with the other. In order to do this, you have learned, I hope that you have learned in physics or in thermodynamics, that there were some relationships that have been explored. So, for example, there is the relationship that links the pressure, the temperature, the enthalpy, and the volume. Okay, and this is, for example, the Clapeyron equation that the people have observed. So the researchers and the thermodynamicists have observed, and that allows to represent the observations. Okay, there are also other people that have done that have developed experimental correlations. So it means that, for example, we have realized that the Cp is not a constant. So the specific heat is not a constant. It depends on the temperature. Okay, and that's mainly because inside the molecule, the atoms can also move one with respect to the others. Okay, so it means that the specific heat is indeed a function that can be quite complex. So here I have 5 parameters that represent the relationship between the Cp, for the Cp as a function of the temperature for a given molecule. Okay, And people have made experiments, so I put the constant pressure, and then I'm looking at this, the variation of the temperature as a function of the enthalpy that is received. And I'm doing it for different temperatures so that I will be able to represent, to calculate A, B, C, D, and E. And this will be then stored in a database that will then be shared by the rest of, with the rest of the world, so that we will be able to calculate the specific heat as a function of the temperature of a given molecule. Okay? There are, however, some difficulties related to this, is that the number of compounds is more or less infinite. Okay, we know the very simple ones, so the oxygen, the hydrogen, the nitrogen, etc. But as soon as you go into trying to characterize what is the CP of the gasoline, for example, that you have in your tank, you will realize that inside your tank you have not a single molecule, you have a collection of molecules. And the collection can be very big because it might also happen that as soon as you link atoms together, there's what we name the isomers, so it means the same number of atoms, but with connections at a different place. If there is a connection in a different place, it means that the agitations will be different and the CP will be different, right? So for the standard compounds, these data exist, but sometimes not all the values are available. And there exist techniques that allows them to estimate what will be the value of those parameters, so that A, B, C, D, and E, by analogy between different types of molecules. And this allows to do the extrapolation if we do not find the values in tables. So where are those tables? The NIST, so the National Institute of Standard from the US, has a very big collection of values for different compounds. So if you go to the webbook.nist.gov/chemistry, you will be able to choose a different compound, a given compound, and they will give you the properties that are known for this compound. Okay, so this is a reference. If you have to make a quick calculation, go there, and you will have the information, right? So this is one possibility. The NIST is also proposing some tools like RefProp, or there is also another one that is CoolProp, which is mainly for, so RefProp is for refrigerant and CoolProp is for the refrigerant as well. CoolProp is open access, RefProp is proprietary. Okay, they use the data that are in the webbook here and allow you to make calculations about properties of pure compounds, mainly for thermodynamic cycle calculations. Okay, so I would recommend you to look at those software if you want to do calculations. Okay, and there exist hooks that can be used in MATLAB, for example, to call those property package, okay, which allows you then to have access to the calculation in if you have to do calculations by yourself. Okay. However, when we have to make calculation of flow sheets, something that is important is that we have to be sure that we are going to have a set of equations that is generic. Okay, because if I have to make a calculation, if you have to program something with a given for calculating, for example, a heat pump cycle, okay, it would be nice that you write only once the function that calculates the refrigeration cycle, and not have to change the full programming if you go from one refrigerant to another one, so carbon dioxide to ammonia, for example. Okay? So what does it mean? It means that it would be nice to have standardized forms of equations. They would then allow us to calculate not only the composition and the states variables for a single compound, but that would also allow us to calculate mixtures. I give you carbon dioxide and nitrogen and ammonia. What will be the performance of the system? Okay? And I'm changing the composition, what is going to happen? Okay? So it means that we have to be able to model mixtures and not only single compounds. Okay? And we have to be, and those methods will be based on what we know. And what we know is the thermodynamic theory. So it means that we would like to have a collection of very nice mathematical formula that are always the same, that can be handled by solvers. Okay? Because I would like to be able to calculate the enthalpy when the temperature and the pressure is known, but I would like also to know the temperature when the enthalpy is known. So it means that I have to be able to use a solver to solve this equation. And therefore, I can also develop very specific methods for each of the equations if the equations is not changing. Okay? So what we are going to do then, therefore, is that we are going to write generic formulations that will allow us to calculate the thermodynamic properties, and then we will adapt the formula by using different values for the parameters that are representing what is in the mixture. Okay, so it means that if I'm going back to this equation here, so the equation here will always be the same, so the CP formula will always be the same. But if I'm computing with oxygen, with nitrogen, or with water, I will have A, B, C, D, and E that will be different, and that will come from a database. Okay, so I write once the equation of the CP, and from there I will be able to calculate the values for any compounds if I have a database. So that's what we will do. And if I do not find values in a database, then I need to have something that allows me to estimate what is the value if the information is not there. And this is if I'm satisfying those two characteristics, so a generic model and a database of parameters, then I will be able to calculate the thermodynamic properties of any of the state that my process units are going to deliver. So we'll be able to calculate the enthalpy, the entropy, the phase state of the system. Okay? So this defines what I need for defining what I'm naming the constitutive equations. Okay? Do you have questions? If not, then I'm making a break now, and I'm going to start again in 15 minutes, where I'm going to show you those equations. Okay, so now we are going to analyze, and I think it's the part of the course where we will have the biggest amount of equations. What I'm going to show you, which is something that is going to be explained in less than 45 minutes, is in fact a complete lecture that I had when I was studying chemical engineering, because the thermodynamics is a key for the chemical engineering. However, so what is important here is that we have realized that we need equations and we need parameters. So I'm going just to show you what are the types of equations to just, in order that you understand what it means. Okay, I don't want you to have to know those equations. I don't want you to study them in detail, but I want you to be aware of what is behind the equations that you are going to activate and that will be written for you, and that will be solved for you when you will use flow sheeting tools. Okay, so it's just what is behind, and I think it's always important to understand what is behind. Okay, so those are the equations that allow to calculate enthalpy. If I have to calculate the enthalpy, I know that the enthalpy is in fact obtained by summing up the contributions of each of the compounds with this enthalpy of formation, and then the integral from a reference temperature to the temperature at which we are of the sum of the contributions of the Cp of each of the compounds multiplied by the fraction of each of the compounds with respect to the temperature. And the Cp here is in fact a formula we use with here 4 parameters. Okay? So, and what is interesting is that I know how to calculate analytically this integral, because you have learned how to calculate integrals. Okay, so it means I will have an analytical formula that will give me the value of the enthalpy. And of course, if I have only A here, then we go back to what we know, that the enthalpy is in fact calculated with respect to a reference. And sometimes the mechanical engineers make the wrong assumption of considering that 0 degree C is the reference, and therefore they will write that the enthalpy is CPT. Okay, CPT means that the T0 is equal to 0, means that the Cp is just a constant with respect to the temperature. Otherwise, you will have Cp, T squared, T4, T3, T4, etc. And of course, something which is important here is that it might happen that the C here is going to be a negative value, which means that the formula will not be something like this, but will be something like this. Okay? And this depends on the quality of the compounds that we are using. Okay? Now, if I had to calculate I have the way to calculate the gas. This is the formula for the liquid. And you can see that the liquid is going to follow the same expression. And I can even calculate the enthalpy of the liquid based on the enthalpy of the gas. So it means that I can say that the enthalpy of the liquid is in fact the enthalpy of the gas minus the heat of vaporization at a given temperature. And if I have a formula like this one, for example, that is defining the variation of the enthalpy of vaporization as a function of the temperature, then, and it is, you can see that it's a formula that is based on the properties of the fluid, then I will be able to calculate the liquid based on the enthalpy of the gas. Okay? It's a mathematical formula. That's what is important. And if I'm in between, I will have to calculate the fraction that is in the liquid state and the fraction that is in the gas state. So how do I calculate the entropy? Let's go back to the thermodynamics. The thermodynamics is telling us that the variation of the entropy is equal to the Cp times the variation of temperature divided Cp divided by T, multiplied by the variation of temperature, and then the variation of the volume divided by T at constant pressure times the variation of the pressure, which allows me to calculate the entropy. Okay, and you can see that it depends again on the Cp. Okay, plus a value that I have to find in the literature, and something which is then, if I'm in the gas state, that is just related to the constant of the perfect gases and then of the ratio between the pressure and a reference pressure. So it means that if I have the correlations like the Cp, if I know the thermodynamics, I'm able to calculate the entropy, the enthalpy, and all the other properties in the same way. When I have something which is important is that I have to know what is the relationship between the different between the pressure, the temperature, and the volume, maybe. Okay, and I know that there is if I have pressure, temperature, and volume, I have something that needs to solve the problem, and we know the link. So for example, the perfect gases tell us that the PV equals nRT, N being the number of moles, this is the constant of the perfect gases, temperature in Kelvin, the volume, and the pressure. Which means that now I can create a link between the pressure, the volume, and the temperature, okay? Which eliminates the degree of freedom that I was looking for, right? Okay. Now this is the perfect gases, so it's a perfect situation where the molecules do not interact a lot, so it works with low pressure and simple molecules. In fact, we know that the molecules will have an attraction and a repulsion term, and this leads to an equation like this one, which is the van der Waals equation that you probably know. And you can see that we retrieve the basic equation here, okay, but there is a perturbation with the A and the B and the impact of the volume here, okay? This is what has been observed by people, okay, and they have deduced an equation. So what is important here is that the form is coming from what we have observed and from the work of a lot of scientists, and it's not just a polynomial, okay? It's a real formula here, okay? That's very important. The knowledge is here. This is the artificial intelligence, okay? It is based on the data observations, and the people have discovered this kind of formula by trying to describe what is happening inside the system. And the people have improved the formula. So this is the Redlich-Kwon equation of state, this is the Soave one, this is the Penck-Robinson one. Okay? So you can see that all those formulas are more or less following the same principle based on the van der Waals equation, but with some different influences, okay? We know that, for example, in the Soave, the term here is a function of the temperature. You do not see the V square, but you have a B term here that is appearing, okay? So this is mainly because the people have observed with a lot of compounds the behavior of the compounds as a function of temperature, pressure, and volume, and have been able to define this. Now, one of the questions is, how do we calculate the value of A, and especially in this situation, for example, how do we calculate the value of A and B? So, and there is a way that is based on what we know from the thermodynamics. There is a special point in which is the critical point, so the top of the curve, okay, in which we know that the variation of the pressure at this temperature as a function of the volume is equal to 0, as well as the second derivative at this point, which gives me, in fact, two equations that allows to calculate the A and the B. Okay? And this is a condition. So it means that the A and the B are not, cannot be chosen arbitrarily. Okay? They are related to conditions that refers to the calculation of the critical temperature. So it means that if I give you the critical temperature, you are able to calculate the A and the B. Okay? And when you have something that depends on the temperature, then you have to do some, you need other information to fit the curves. Okay? Something which is very important here is that as soon as I have those values, so the A and the B formula here, something that is interesting is that I will be able to deduce what is the value of the enthalpy. Okay? And what I'm doing here is that I'm just applying what we have learned in thermodynamics, relationships between state variables for a given state and for the given compounds in given conditions. Okay? The other dimension that is really interesting is that the value of A and B can be related to the composition. So there are rules that give us the value of A and B when the composition is going to change. So if I have more ethanol in water or less ethanol in water, so ethanol in water is beer. Huh? If I have more ethanol in water and less ethanol in water, I will have another behavior with respect to the evaporation. Okay, and this is you can calculate the values that are in the formula that I have. That is here. So the A and the B that allows to calculate everything, right? By applying mixing rules. And those are the mixing rules that are applied. And there is here a special term which is representing the interactions of the different molecules. So it's a binary coefficient which is related to the compound A and the compound G, which is related to the characteristic of the two compounds when they are alone, so not seeing the others, plus or multiplied by this coefficient here, which is what we name the interaction coefficient, which is going to represent how the two molecules do interact one with the other. But something which is very important here is that knowing this value here, I will be able to calculate A and B, and knowing this, I will be able to calculate all the properties that are here. Okay? And among those properties, one that is very important is to know what will be the composition, what will be the state, if I am in the gas or in the liquid state. And if I am in the gas and liquid state, so if I have ethanol and water, what I would be interesting to know is what will be the composition of the amount of ethanol that will be in the gas state, that means is going to evaporate, and the amount of ethanol that is in the liquid state, remains in the liquid. When I'm leaving the beer here, I would like to know how much of the ethanol and how much of the water is going to evaporate and how much will remain in the liquid state. Okay? For doing this, there is, I'm going to use one property that is named the fugacity. It is the trend that a molecule has to leave the state in which it is. So the fugacity of water is the tendency that the water that is in the liquid state wants to go into the gas state. Okay, and for a moment I know that I'm releasing water in the atmosphere. You do not see it, but if I'm shuffling on the window, you will see that there will be vapor that will condense on the window because the window is colder, and therefore some of the molecules that are in the gas state, if they see a lower temperature, they will want to go in the liquid state. Okay, so this is what is named the fugacity. And what I'm going to say is that if I have a mixture, I'm going to express that if I'm at the equilibrium, then the composition in the gas state, which is what we name the fugacity in the gas state, will be equal for each of the molecules in the system will be equal to the fugacity of the liquid state. Okay, so it means that the molecule, when I'm leaving the system alone, will be in equilibrium in the sense that it will have the same interest to leave to go from the liquid to the gas state, then the interest to go from the gas to the liquid state. So this is the equilibrium, goes in both directions. Okay, and this is depending on the composition in the gas and the liquid state, which allows me then to express the coefficient of separation between a molecule that will have a tendency to go in the gas state with a certain composition, so occupy a certain volume, and in the liquid state, where it will also try to occupy a certain volume. So the more volatile the fluid will be, the compound will be, so the highest, the interest for it's to go into the gas state, the highest will be the Y, and the lowest will be the X. Okay? And by expressing the equilibrium, what I can see is that this ratio of separation is a function of what we name the fugacity. The fugacity is a function of the saturation pressure. The saturation pressure can be calculated by a very nice formula like this one. Okay? And the coefficient that is here can be calculated by this kind of formula that I have, in fact, in more detail here. So, knowing the equation of state, I'm able to calculate by all those values here, which are all depending on the two parameters that I have here. Okay? I will be able to calculate the phi here, which will then be used in order to calculate the ratio between the amount of the compound that will be in the gas state and the amount of compound that will be in the liquid state. Okay? A single equation calculation of mathematical formula based on a very limited number of parameters that most of them depends only on the single compounds. Okay, so it means that as soon as I have those values coming from a database, then I can do everything. Okay, with just one that depends on the interactions here. Okay, but the advantage of doing this is that I will be able to calculate what is the amount of ethanol that is going to be in the gas state, what is the amount of ethanol that is going to be in the liquid state, and this allows to calculate the distillation. Okay, so it means that if you allow me to calculate how much heat I will need to put into a distillation unit in order to increase the alcohol content of the prune or the apricotine. Okay, so back to the basics, huh? But this is the reality, and what is important here is that it is based on a very limited amount of information, and I'm really applying what the scientists have observed in the past to be able to write those very complex equations here. But you can see that this complex equation is in fact a mathematical processing of a very simple expression, okay, which is a thermodynamic expression, right? So it's really interesting because then it allows me to calculate, for example, the equilibrium of a mixture, okay? And this can also be done for the chemical reactions. So not only for physical separations, but also for chemical reactions. So it means that I can estimate what will be if we leave the time. Chemical reactions have also kinetics, but if they are in equilibrium, we can calculate with only the values of the elements in the equation of state the equilibrium. The equilibrium being the place where the Gibbs free energy is minimum. Okay, it will go back to the equations that you know from the past, but this can be calculated directly by using the properties of the equation of state and the parameters. So this is really powerful and allows to make calculations of distillation columns, of separators. So if I'm mixing two fluids and then I want to know what is the gas in the liquid state, this will be calculated by this way. So remains one question. So where do we find the values? So I have already explained that the values can be found in thermodynamic databases. I have shown the NIST database, but there are also the ASHRAE that is compiling values, the DIPPR which is also another thermodynamic database, where you will find the value of A, B, C, D, E. Humans have, however, been facing the problem of having to calculate the values for millions of compounds. So if you look at the number of compounds that you have inside your body, okay, if you look at chemical formulas, then it's a very huge number. I do not have the real number, but it's very huge, because any of your cells has a lot of different chemical compounds. Okay, so it means that we have to be able to extrapolate or to estimate the value of the A and the B that I was presenting before. Okay, in a systematic way. Something which is quite interesting is that, and again, it's based on the intelligence of the thermodynamicists. They have made an analysis and they have finally realized that something that was really important to know is the critical conditions. So the place where the density of the liquid is equal to the density of the vapor. So it's characterized by the critical temperature, the critical pressure, and the critical volume. And to a factor that has been identified, it's named the acentric factor, that is calculated by this formula, that is going to characterize each of the molecules that we have. In addition, I need to know what is the boiling temperature and the fusion temperature. And if I have those values, then I will be able to make extrapolations of all the other properties. How do I do it? And why did the people realize that it was really important? It's mainly because they realized that we can work with thermodynamics in reduced conditions. The reduced conditions are the conditions in which the pressure is not anymore the pressure, but the pressure divided by the critical pressure. The reduced temperature is the temperature divided by the critical temperature. And what the people have observed, and I'm showing you here for 3 different types of compounds, or 4. So you have here methane. Those are the triangle. The star is ethane, the circle are propane, and the black circle are butane. And what they have observed is that when they were looking at the relationship between the compressibility factor, so it's Z, it's PV divided by RT, okay, for which measure the level of non-perfect gas, okay? And they have been showing that if you plot this value as a function of the reduced pressure, you can see that the curves are exactly the same, okay? So this is an observation, but it means that if I'm working with the reduced conditions, I will be able to calculate the Z, the compressibility factor for the different compounds with exactly the same formula, right? And from there, the people have then deduced a relationship that allows to estimate the value of all the different coefficients that we have as a function of known coefficients by applying the formula that is here, that is going to say that if I know the factor, which was the one that I have introduced here, so the acentric factor here, for a compound that is a characteristic of the compound, if I know this factor, then I will be able to calculate any of the properties by mixing, by comparing, by analogy of this factor with respect to known molecules. And the known molecules are typically selected with 2 different acentric factors. So on the one hand, the one that is nearly 0 and another one that is nearly 1. It's the one for argon and for butane. And by using this weighting trick that is here, okay, I will be able to calculate any of the properties of any of the compounds based on the fact that I know the property of the compound for argon and butane. Okay. This is the trick of the corresponding states that allows me to estimate what will be the properties if I do not necessarily have access to all the compounds. Okay? And this then allows to, for example, write the equation that I have shown before with value of A and B that are calculated by this equation. So A is a function of T, but it is in the reduced space and is a function of the acentric factor. So it means that if I know the acentric factor of any molecule, and this is a value that you will find in the literature, you will be able to apply the equation of state. Okay? Which then means that you will be able to calculate mixtures, etc., etc., etc. So you will be able to calculate entropy and enthalpy. Okay? So it means that now I will be able to make the calculations. Okay? I will be able to calculate the all the thermodynamic properties, to calculate those kind of curves, and I have the mathematical formula that allows to make those calculations. Okay, so no need anymore to go in a book to see a graph or on the internet to see a graph. I have the possibility of calculating any point of those curves here, for any compounds, provided that I have a minimum amount of information. The minimum amount of information being, I recall, the minimum amount of information is the critical temperature, the critical pressure, the critical volume, the acentric factor, and the temperature of evolution. By knowing this, I will be able to calculate the thermodynamic properties. Okay? So now I will be therefore able to I will therefore be able to make the calculations of all the points in my flow sheet. Okay, provided that I have the model that gives me what is the amount of energy that has been transferred, what is the pressure, how is the pressure going to be increased, etc. Okay, which will allow me to make all the calculations that I need. There are still some remarks, and one of the remarks is the difficulty that can be observed in the mathematical formula. In fact, when I was saying that if you give me the temperature, the pressure, and the composition, I will be able to calculate the enthalpy, and everyone has said yes. Unfortunately, it's not necessarily true. It's sufficient, but not. It's necessary, but not sufficient. If I give you the temperature and the pressure of water, and I give you 1 bar and 100 degrees C, you will not be able to give me the enthalpy. Okay, why? Because the enthalpy for a given temperature, the enthalpy is unknown. I know that the water is boiling during the evaporation, the temperature is constant. So it means that sometimes we will have to choose values to represent the state, which will not be the temperature and the pressure. In the case of the tool that you are going to use for the flow sheet, you will in fact use the enthalpy and the pressure as a reference, and not the temperature, because it's not possible always to calculate the enthalpy for a given temperature, but it is always possible to calculate the temperature if I give you the enthalpy. Okay, so it means that sometimes we have to just be careful about which state variables we are going to use. Okay, so it means that now I have shown you that we have a tool which is named the constitutive equation, that is able to calculate the thermodynamic properties of a state as soon as we fix the value of n plus 2 variables, which are the degrees of freedom. The n plus 2 have an additional constraint that it needs to have one extensive variable in the list, because I need to have something which is going to fix the flow. And from this, I will need to have the equations. So I have to choose the equation of state. And when you will use Valley in the coming weeks, the first step you will have to do is choose the compound and choose the mathematical formulation. By choosing the compound, in fact, what you will do is that you will ask the system to go in a database. And the system will go in the database and will look at the values of the critical temperatures, volumes, pressures, and acentric factor of the compound. And then afterwards, you will have to select what is the mathematical formula to be used. And you will be offered the Soave, the Bank-Robinson, or whatever. You can choose this value and even change from one equation to another one according to what you want to calculate, because sometimes some equations of state are more precise for the equilibrium than for the enthalpy calculation, for example. You will have to choose the mathematical formula and the database that you are going to use. And from there, you will be able then to apply the calculation of the equations of the process units, because now you will be able to know what is the state that is here, with the enthalpy, with the entropy, etc. And you will be able to calculate what is the state here and how the states have been transformed by applying the mass and the energy balances, but also by representing the performance equation. So for example, if you calculate a compressor with an isentropic efficiency, you need to be able to calculate the isentropic conditions, and this will come from the equation of states and the constitutive equations. Okay? So it means that you will call the thermodynamic model, ask what is the value of the entropy there, what is the value of the enthalpy there, what is the temperature when the entropy has this value, and from there you will be able to make a calculation of the compressor. Okay? Do you have questions? Yeah?
In the previous slide, it says at least one intensive variable, but...
no, it's extensive. You're right. No, you're right. It's one extensive variable. So there is at least one that needs to fix the flow. Okay? Otherwise, so it means also that if you fix the temperature, the enthalpy, let's assume that you have only water. So normally you need to fix 3 values, okay? But you cannot fix the temperature, the pressure, and the enthalpy, the specific enthalpy. But you can fix the temperature, the pressure, and the total enthalpy. Because the temperature and the pressure will allow you to calculate the enthalpy specific, and the total enthalpy will allow to calculate the flow. And it's an extensive variable. Okay? So I have to make the corrections, and I'm going to do it also directly now. Okay, other questions? If not, this afternoon you will have to work on the optimization. So TV and Alessio and Rafael and Julia, Luis will be there to help. Do not hesitate to ask questions, and also do not. So today I have to leave, but if you want to discuss with me, do not hesitate. So you can ask me. So officially I'm here. Okay, so it means that if you want to discuss the results, for example, that you have with me, just raise your hand and say, okay, can we have a chat on to present the results? I'm here. Okay. Ok, son bon appétit alors.